Architectural Design, Chapter 6, Sommerville. Architectural design is concerned with understanding how a system should be organized and with designing the overall structure of that system. This is the first phase in the design input, and the output of the phase that will be the architectural model. This chapter deals with architecture of individual programs, sometimes referred to as architecture in the small. Later on, we'll look with architecture in large complex systems or architecture in large, which we did see a little bit in the last chapter. So there are many advantages to producing an architecture for the system. One is stakeholder communication. Second is systems analysis. How do the different pieces fit together? You have large-scale reuse through design patterns. And it can serve as a design plan for negotiating system requirements and as a means of structuring the discussion for future requirements, or in agile parlance for future sprints, potentially shippable product increments. And really in summary, managers like pretty pictures. You actually have to think about this before you go ahead and code it, which is a good side effect. And you also get something known as product line architectures, which is an emerging area of software engineering research, where you have something that can be reused over and over again. And again, architectural design can also be important in agile methods or agile-based approaches. It's generally accepted that an early stage of the agile process is to design the overall systems architecture. Refactoring the system architecture itself is usually pretty expensive because it affects so many components. So, you want to make sure you get it right in the beginning. We'll begin our architecture design with the simplest of tools, the block diagram. So this is an example block diagram. Figure 6.1 on page 154 of the 10th edition, and it's a robotic packaging system. Basically, it picks things off the conveyor belt and uses its vision system to pick the right type of packaging. This diagram shows the components that need to be developed and how they relate to one another. In the earlier edition, Sommerville discusses some of the controversy over whether to use UML, architectural description languages, or simple diagrams. He sides with the agile folks who posit that using simple and informal diagrams as opposed to a more formal approach saves time and still communicates the central ideas behind the development. So the choice of architecture depends on, to a large degree, the non-functional requirements. If you're going for performance, you want the components to have as little communication as possible between them. So that means making larger grain components or larger components and not having as many small subprograms. If you want to go for security, you want a layered structure with critical assets located at the inner layers where they're more difficult to get to. For safety, you want to locate safety-related operations in a single subsystem or a small number of subsystems to prevent failures. If you're going for availability, you want a large number of redundant components, and maintainability, you want the small, fine-grained, self-contained components that can be readily changed, and that kind of goes to the opposite of the some of the other approaches. Obviously, you can have conflicts over the design based upon which requirements you stress. For example, if you want performance and you have a few large components, and maintainability, several small fine-grained components, you need to decide what's more critical to the system, the performance or the maintenance. And it's a conversation that you can have with the product owner. Subsystem design basically is decomposition of the system into these large grain components, each of which can be a substantial system in its own right. Not necessarily great for developers, but it's a good thing for managers and clients. You want to try to decompose these subsystems based on logical grouping of the requirements, and we'll see that in some of the architectural design decisions. And system decomposition in general is a difficult problem. So what are some of these architectural design decisions? Well, there are about 6 or 7 of them here. This is figure 6.2 on page 157. So first, is there a generic application architecture that can be used? Systems in the same application domain often have similar architectures, and they reflect the fundamental domain concepts. How will the system be distributed? You need to consider parallel and distributed system architectures if it doesn't run on a single machine. In other words, how will the components be divided amongst different machines? This is covered in a later chapter, so we're going to gloss over that decision for now. What architectural styles are appropriate? Architectural style is a pattern of system organization, such as client-server or the OSI model. You may remember the 7-layer model from your networking class, or you'll be exposed to it in your networking class that takes place in the coming terms. What approach will be used to structure the system? You have to choose the most appropriate structure to meet the requirements. How will it be decomposed into modules? Again, this is a tricky question to answer, but you need to come up with a general strategy for how you're going to decompose it. What control strategy should be used? How is the execution of subsystems controlled? How will the architectural design be evaluated? You can think back to the non-functional requirements again. Which one do you decide is most important? And how should the architecture be documented? Sommerville proposed an architectural design document that includes several different models. So the architectural design document models are a static structural model, show the major components. Dynamic process model will show the process structure of the system. Interface model will define the subsystem interfaces and how they connect to one another. And the relationship model, such as data flow, shows the subsystem relationships. Finally, the distribution model shows how the subsystems are distributed across the different computers. Of course, the true test of an architecture is how well it meets the functional and non-functional requirements of the system. It's impossible to represent all the relevant information in any single architectural model, so you should have multiple views, such as the logical model, the process view, development view, and a physical view. And we'll talk a little bit about architectural patterns, which are basically stylized abstract descriptions of good practice, which have been tried and tested in different systems and environments. The idea behind patterns is to present, share, and reuse knowledge about software systems. So, why reinvent the wheel? Or good writers borrow, great writers steal. And the picture here is Ted Berrigan, and the quote, good writers borrow, great writers steal, has been attributed to a large number of people, T.S. Eliot, Oscar Wilde, etc. However, I think New York poet Ted Berrigan took the advice quite literally and stole books from bookstores. In particular, he would steal books that his friends had written, have them sign them, and then sell them back to the bookstores for a profit. Berrigan also said, whatever is going to happen is already happening. So, pretty cool guy. Speaking of things already happening, Gamma's Design Patterns book, on which a lot of this lecture is predicated, was the impetus for this idea nearly 25 years ago in 1995. So, what are the 5 architectural patterns that Sommerville talks about? Well, 1 is the layered architecture, 2 is the model view controller, 3 is the repository architecture, 4 is the client-server architecture, and 5 is the pipe and filter architecture. Usually I make this a class exercise, but since it's a flipped classroom, we'll cover the answers in a more straightforward manner. So the model view controller basically separates the presentation and the interaction of the system data. So there are 3 components that interact with one another. The model component manages the data and the associated operations on the data. The view defines and manages how the data is presented to the user, like the user interface. And the controller, which are the events, manages user interaction. An example, key presses, mouse clicks, and passes these interactions to the view and to the model, which are then updated. And so this is used a lot in graphical user interface development. It's good because it allows the design to change independently of the representation and vice versa. Supports presentation of the same data in different ways, with changes made in one representation shown in all of them. Problem is it can involve additional code and code complexity, even when the data model and interactions are simple. Think iOS as compared to Visual Studio, Visual C# development. So this slide obviously came from Sommerville. This is figure 6.5 on page 162, and it's an example of the model view controller. Here, the model component manages the system data and the operations associated on that data. The view component defines and manages how the data is presented to the user. So the model is the internal representation, the view is the external representation. So the view can query the model to see how to display the underlying data. The controller maps the user actions, for example, a button click to update the model, and which also updates the view. An example of a model view controller is one for a web system using this design pattern. As before, the model component manages the system data and the associated operations on that data. The view component defines and manages how the data is presented to the user, and the controller component manages the user interaction as before. Key presses, mouse clicks, etc. and passes these interactions to the view and to the model. Another common design pattern approach is the layered architecture pattern, and this basically organizes the systems into layers. A layer provides services to the layer above it and distributes things to the layer below it. So it's used to model interfacing subsystems that organizes the system into a set of layers or abstract machines, each of which provide a set of services to the one above and below it. It supports incremental development of subsystems in the different layers, and when the layer interface changes, only one layer is affected, the adjacent layers. The separation allows for localized changes, and the layer pattern helps to achieve that. The major drawback is it's usually artificial to structure systems in this way. And we're going to see this with the OSI model. I'll cover a little bit of it, but I'll save the details for the networking class. So here's a generic layered architecture. You have the user interface on top. That works with the user interface management, authentication, and authorization, which allows you to access core business logic, application functionality, and system utilities, which that layer interfaces with system support, for example, the operating systems, the databases, etc. Sommerville includes example for a specific online learning system that he developed as part of his book. And obviously the OSI model is the most famous of all layered architecture. We'll see it in one of the later slides. However, I'm again going to leave the details of that to your networking class. Another common design pattern is the repository. All data is managed in a central repository that's accessible to all the different system components. They don't interact directly, they only act through the repository. So this pattern is useful when you have a system with large volumes of information that's generated and stored for a long time. You can also use in data-driven systems where the inclusion of data in the repository triggers an action or tool. It's good because components can be independent. They don't even need to know about the existence of the other components in the system. Changes made by one component can be propagated to all the components, and all data can be managed consistently. That is, all backups are done at one time, and it's all in one place. The drawback to this one is there's a single point of failure, so problems in the repository affect the whole system. There can be inefficiencies in organizing all the communication through the repository, I think that central choke point. And distributing it across several computers can be difficult. So that's a difficult design problem. So here's an example of repository architecture for an integrated development environment. The project repository has everything for the project, which can be generated by UML editors, code generators, the Java, Python editors, report generator, design analyzer, and design translator. But it all goes into a project repository that can be accessed by each of the individual components, or they can access what's appropriate for each component from that project repository. Another famous design pattern is the client-server pattern. The functionality of the system is organized into services, which each service is delivered from a separate server. Clients are users of these services and access the servers to make use of them. For example, there's the film and DVD library that we'll see on the next slide. And this is used when you have a shared database and has to be accessed from a wide variety of locations. Because the servers can be replicated, they may also be used when load on the system is variable, so you can get things like load balancing. And the good about this is that the model can be distributed across a network. General functionality can be available to all clients, for example, printing service, and doesn't need to be implemented by all the services. Each service does represent a single point of failure, so this is susceptible to denial of service attacks, or if you have a server failure. The performance can also be unpredictable because it depends on the network as well as the system. And so, there's a lot of latency and variability in network access. So, you can't really predict the system as well. And there can be management problems that the servers are owned by several different organizations, which seems to be more and more common. So, Sommerville does love his library systems, and this is an architecture for a film library where clients access the catalog server, video server, picture server, and web server from over the internet. And they can basically access all of these different services that are hosted on different servers. So the catalog server and library catalog may be on one server, whilst the web server and the film and photo video are on a film and photo information are on a second server. This is figure 6.13 on page 168 of the 10th edition. Older design pattern is the pipe and filter pattern, and basically this is deals with the processing of the data. It does have its use in business, and so it's important to know it. Basically, you have functional transformations of process inputs to produce outputs. This can be referred to as pipe and filter model, as in the Unix shell systems, and variants of this approach are pretty common. When transformations are sequential, this ends up being a batch sequential model, which is extremely useful in data processing systems. This one's not really tremendously useful for interactive systems. So here's an example. This is still from the 9th edition. The 10th edition version of this cuts out a lot of the details and only shows a subset of it. And this is basically a batch processing system for invoices that basically sends out receipts and reminders to people that, hey, you either paid your invoice or you need a reminder to pay your invoice. And again, these pipe and filter systems work very well for batch processing systems. So application architectures are basically designed to meet organizational needs. Businesses have a lot in common. Their application systems also tend to have a common architecture that reflects various application requirements. So a general application architecture is an architecture for a type of software system that can be configured and adapted to create a system that meets specific requirements. For example, SAP and PeopleSoft. A lot of different organizations have supply chain management, which can be accomplished via SAP, and a lot of different organizations have human resource functions, which can be accomplished using PeopleSoft. And I do wish these guys would pay me for putting their logos on the slide, but they are good examples of application architecture or application product lines. There are three broad types of application architectures, or four actually. Data processing applications, which process data in batches without explicit user intervention. Transaction processing applications, which are data-centered applications that process user requests and update the information in the system database. Event processing systems, where system actions depend on interpreting events from the system environment. And language processing systems, where the applications are specified in a formal language that is processed and interpreted by the system. Let's take a look at some more detail. The transaction processing systems process user requests for information from a database or request to update the database. From a user perspective, a transaction is any coherent sequence of operations that satisfies the goal. For example, I might want to find the times of flights from Hilo to Maui, or I might want to withdraw money from an ATM. Either one of those would represent a transaction. Users make asynchronous requests for services, which are then processed by a transaction manager. So, for example, the ATM system. The ATM itself would get my customer account ID, validate my card that it's actually a card from the issuing bank, and allow me to select the service. Say I want to get $20. The database would query the account, see if I had that $20 in there, and update the account, which would send it back to the ATM for processing. It would print the details, hopefully dispense my $20, and return my card. Information systems also have a generic architecture that can be organized as a layered type of architecture. These are transaction-based and they usually involve a database. The layers typically include user interface, communications, information retrieval, and the back-end database. So, for example, here's this mental healthcare system. It's page 174, figure 6.19 of the 10th edition. And this system is modeled using a layered approach. The top layer is the web browser. The next two layers are the application layers, where you log in, check what role you're assuming. You have your form and menu manager and data validation. That ties into security management, patient information manager, import and export and report generation. And then at the back end, at the bottom layer, you have your transaction management and patient database. Language processing systems accept a natural or artificial language as input and generate some other representation of that language. You can think of this, for example, as a compiler that would take your third generation programming language and turn it into machine code. Or it could include an interpreter to act on instructions in the language that is being processed. Used in situations where the easiest way to solve a problem is to describe an algorithm or describe the system data. So for example, here's a language processing system. I have my source language instructions. The translator checks the syntax and semantics, and it will generate abstract machine code instructions, which will be sent to the interpreter, which will cover the fetch, decode, and execute, and also retrieve the data necessary to run the program, and this will produce results. You've probably seen this to death in 150, 151, 321. So older architectural patterns, these are some captures from older editions of Sommerville. I've left them in here since they may be of interest to you. And there's still something to be learned from these older patterns. So this one is a call return model. You'll recognize this from CS 150 and 151. You have your main program, you have your different subroutines or functions that can call other functions, and eventually pass that data back to the main program after they return. Centralized control model, basically you have a central control, and you have sensors and actuators. Sensors are things that receive information from the environment. Actuators are things that act on the environment. And the system controller deals with the computation processes, the user interface, and the fault handler. So this is very good for embedded systems. Control model based on selective broadcasting. You have event and message handlers that send statements or messages to various different subsystems. The interrupt-driven control, again, this is one that's good for hardware. You get interrupts. These go to interrupt vectors that pass them off to the appropriate handlers that call the appropriate processes, and the good old OSI model. These are the 7 layers that are necessary for the network: the application, presentation, session, transport, network, data link, and finally the physical, the actual hardware. Either copper or fiber optic wiring, or the Wi-Fi that sends the data across. And you'll get to see a lot of this in CS 431. And last but not least, this is the reference architecture for ECMA, which is a tool for managing case tool support for software engineering. The idea behind this is you would have various tool slots that you could put in. These would be case tools for assisting with software engineering, and then you would have basically message services that pass between those different tools in the data repository and the user interface. This is the dream. In reality, we never quite went to this. It was an idea for an architecture once upon a time. So the next time we'll look at design and implementation using unified modeling language.